Hey guys, welcome to the video. Today I'm going to make a video about electrophilic substitution reaction. And in this tutorial, um, I'll just show you the halogenation first of all. And later on, we'll also make a couple more videos just to show you that different other reactions using this same electrophilic substitution mechanism. So if you remember correctly, probably have seen this before, that when we have an alkene, and it reacts with bromine, it gives a product like this. And this is an addition reaction. This is an addition reaction. Well, we have our double bond here, and when we have pi bonds, which means that this alkene has higher electron density, and this can act as a nucleophile. But in this reaction, bromine is acting as an electrophile because two bromine atoms are bonded together through a covalent bond, and they have this electron density around them. And when they come closer to an alkene, the effect actually gives this bromine molecule an induced dipole moment, and that's why it gets partially positive on one side and partially negative on other side. And then it becomes electron poor. And our nucleophile is already electron rich. And as we have one electron rich compound and another electron poor compound, they go into the reaction and we form this product. Now, if you want to make the same reaction, the halogenation reaction, when it comes to the aromatic compound, let's say we have, let me draw it a little bit nicely. We have, I'm sorry. Okay, so we have this benzene ring, and what happens that when it reacts with bromine? Well, no reaction happens. Well, you might say that, okay, we also have like higher electron density here, and this can act as a nucleophile, and we already know that, okay, bromine can act as an electrophile, but why is not this reaction happening? Well, the reason is benzene is an aromatic compound, and actually, if you add the bromine atoms across one of the double bonds, the aromaticity is destroyed, and it loses the stability that it had when it was aromatic, and it doesn't want to do that. But we can actually force this reaction to happen, and we can force this reaction to happen because there are two ways we can actually make a reaction happen, because you already know that a nucleophile is attracted to an electrophile, and this attraction can be tuned. That means that we can actually make this attraction even stronger. And somehow, if we can make the nucleophile much more electron dense, that means a stronger nucleophile, and if we can make an electrophile more electron poor, that means a better electrophile than before, then this attraction between the nucleophile and the electrophile gets stronger. And that can force this kind of reaction happen. Now, how can we make this bromine much more electron poor? Well, you saw earlier that when this bromine comes closer to an alkene, it gets this partial positive charge and partial negative charge on it. But if we can somehow manage to get a positive charge on this bromine atom, this is this is even more electron poor than before. But how can we find this positive charge on a bromine atom? Well, there comes the Lewis acid. There comes the Lewis acid. So I already made a video about Lewis acid. Lewis acid, when a compound wants electron and it can actually accept the electron, that means that it can act as a Lewis acid. Now let's try to make this reaction happen. Let me get rid of this and draw this nicely again, just to show you the mechanism that how this is happening. So you got the idea, right? So you got this idea. Now we have to find a way that how we can get this positive charge on the bromine atom. And let's say that we have aluminum bromide, which is a Lewis acid, because if you look at the structure, so this is the structure, and this aluminum, the central atom aluminum, it's in the 3A column in the periodic table, and it has 3 valence electrons, right? And it has an empty orbital. That's why it can actually accept electron. So let's say that we have the same benzene ring, and we already have our bromine, and we introduced aluminum bromide, the Lewis acid. Now you'll see that we form a product. We form a product like this, which is called bromobenzene. Now, what's the mechanism, right? So let's just draw it like on the right side here, so that you know that how this is happening. So you already know that this can act as a nucleophile. Okay, but we'll just go into that later. Okay, so let's just think that we have this aluminum bromide, and we have this bromine molecule which has lone pairs of electrons on them, right? And this aluminum can accept electron. So let's say that this bromine molecule is donating electron to this central aluminum, because this bromine molecule can act as the Lewis base. So Lewis base is just the opposite of Lewis acid, which can donate electron. So when it's donating, we are forming a complex. So we are forming a complex where we have this bromine. Obviously, one of these bromine atoms is donating electrons, so it will have this positive charge on it. And as the aluminum is accepting electron, it will get this negative formal charge on it. And we already have another bromine here. So we form this complex which can act as the source of this positively charged bromine atom. Now you can see that, right? We got something where we have this positive charge on the bromine atom, which can be a better electrophile, much more electron poor, and which can initiate this reaction here. Now, just to make sure that this complex, you might think that how do you exactly get this positive charge? Well, if you think that let me just change the color a little bit. So this bond actually, you think that this is leaving the electron on it, and so that means this bond is breaking. This bond is breaking, and you get this aluminum here, bromine here. It has a negative charge on it. We have another bromine here, bromine. Now this will get neutral because the positive charge is compensated with the electrons from the bond, right? So it has now all 6. electrons, and then the other bromine is already separated and it already donated the electrons, so it will have this positive charge on it. That's one way of thinking. But actually in reality, this positively charged bromine atom does not stay in the solution like this. Rather, you'll find it as a complex at which comes closer to this benzene ring, and the reaction happens. So let me just get rid of this again, and let's talk about this halogenation reaction and why we call these an electrophilic substitution reaction, because you saw that we call it an addition reaction when we added the two bromine atoms across the double bond. So the first step, there are two steps in the reaction. The first step, we'll just write one. So we have this benzene ring already, and this is the nucleophile. In the first step, the nucleophile will attack the complex, right? For the positively charged bromine atom. So let's say that we have this complex. Let me draw the complex again, right? So you have this aluminum, we have this bromine here, and we have one bromine here. We're just flipping it a little bit just to make sure that we can easily show you how the mechanism is happening, or how the mechanism is actually being carried out. So you already know that one of these bromines has positive charge on it, and the other has all 6 electrons. So this one of the pi bond will attack this bromine atom. This bond will break. This let me change the color again, and this bond will break and it will leave the electron on the other bromine atom. So that means we already are having a positive. If you think about the drawing from the last one, that when this bond breaks, we already have a positively charged bromine atom in the solution. So this nucleophile or the pi bond attacks on the bromine, this bond breaks and leaves the electron on the other bromine atom. So we get an intermediate, which is like this. This hydrogen is not yet removed because we have hydrogens here and here, right? Here. You already know that. But we attach the bromine atom, and now that this pi bond breaks, we have a positive charge here because it donated this electron to this bromine atom just to make sure that it can attach to the ring, and you already have the double bonds here. So this is the intermediate, and we also have our other product here, like this. Okay, so aluminum tetrabromide. Now this intermediate actually can stay in a resonance form, because you see that this positive charge is not static. It's not static, and actually all the electrons inside this ring, the pi bonds, they try to compensate this positive charge, and these electrons are flowing inside the ring, and this stays in resonance. And we can show there are like 3 resonance structures, and we can just draw them. And it's important for you to draw them, because otherwise you can't actually explain how this positive charge is compensated within the ring. And it's a nice way to show that, okay, what is happening when we form this intermediate. So let me draw this resonance structure, which you also need to draw. So we have this, right? We have a positive charge here. We have double bonds here. We still have this proton, and we have this bromine. Now what happens is that this bond tries to compensate this positive charge. So it just try to it just tries to fill the void here, and which can go back and forth. Let me change the color again. I'll just draw this with a black pen. All right. So we still have this benzene ring where this positive charge is compensated. Now we have a double bond here. We already have this H and Br here. Now this place, now it lacks the electron. Now it will be positively charged, but we still have the double bond here. So later on, this one will try to compensate the positive charge here. This one will try to compensate the positive charge here. And you can imagine that what's happening. You can imagine what's happening, right? You can imagine what's happening is that we have the benzene ring. We already reformed the double bond here. We have a double bond here. We have Br here. We have a proton or hydrogen here. And now this place will have a positive charge. So you can see, and they can actually go back and forth because they stay in all these three forms. And that's how we have to draw all these three structures. So they're always in resonance. Now let's think that, okay, we already have this, right? The third one here. Let's say that we have this structure after resonating. Let's say that you can also take this one as well. So let me get rid of something here from here so that I can draw a little bit clearly. Okay, so we already have this structure now. We already have this structure where we have a double bond here, double bond here. We have a positive charge here, and we have a proton here. We have a bromine atom here, and if you can introduce a base which has like this electron and which can actually pull this hydrogen away, then I can reestablish the aromaticity that it lost, right? The aromaticity, because I told before that we actually the benzene does not want to react with this bromine molecule because it will then lose the aromaticity, and it does not want that because it has the stability when it is aromatic. But in the first step, you see that when the nucleophile attacks, when the benzene ring attacks this complex, it actually loses the aromaticity. The aromaticity is destroyed. But that is just temporary thing because we'll reestablish this aromaticity in the second step where the base will come into action. It will pull the hydrogen or the proton away, and later on, this bond between hydrogen and the ring will break, or this carbon will break, and it will leave the electron here to compensate this positive charge, and we will reform this aromatic ring. So that means ultimately the aromaticity is not destroyed. So then you can see here we have our reformed benzene ring, and we already lost the H, and we'll have a product, this bromobenzene. Now you might think, okay, it might be tempting to use B or like bromide ion, right? Because you have a lot of bromines in the solution, and it might be tempting to use one of the bromide ions just to pull this hydrogen away. But that is not actually very intelligent, because if you think about it, bromide ion is a good nucleophile, not a good base. Anyways, you can find a way to find a way where you can actually find a compound which can act as a source for this bromide ion, just like we found a source for Br plus ion. We already have this aluminum tetrabromide in the solution, which can act as a base. And I actually forgot to do one thing here. We actually still have a negative charge on this aluminum, right? Because that's not gone. Because it still has like an extra bond with one of the bromine atoms. So now this will act as a base, right? So let me just get rid of this. It's the color. Okay. We have this complex, or we have this aluminum, we have bromine here, we have bromine here, and let's take that this bromine has 6 electrons on it, and we have another bromine here, and it has a negative charge on it. The electrons from this bond will try to pull this hydrogen away, and this bond will break. That means this bromine will be separated, and it will pull the hydrogen and will form hydrogen bromide in the solution. And now as this bond breaks, we'll also form aluminum bromide again, and we'll no longer have this negative charge on aluminum. We'll form the compound from the start. And you can imagine what happens. This bond will break, and we'll leave the electrons here in the ring, and we'll also lose this positive charge, and we'll end up with the product where we reform this aromaticity, and we'll form this product, bromobenzene. Now, this is not an addition product, because we're not adding like 2 bromine atoms or like 1 bromine atoms here. We're replacing this proton or the hydrogen. We're substituting one of the protons in the ring with our bromine atoms, and this is acting as an electrophile here, the bromine atoms. So this is called an electrophilic substitution reaction.